In this video, we're going to look at how to determine the polarity of molecules with more than one atom. So polar molecules are molecules where the electron density is unequally distributed around the molecule. If we look at water, which has a bent shape, we can see that the electron density is higher here in the red region around the oxygen. And we have less electron density around our hydrogen. So because we have an unequal distribution of our electrons, it sets up a partially negative and partially positive region, giving us a polar molecule. The partially negative region is usually around the more electronegative atom or atoms. Now, nonpolar molecules are molecules where the electron density is equally distributed around the molecule. If we look at boron tetrafluoride, we draw its dot structure. It has a trigonal planar molecular shape. We can see that the electron density is equally distributed around the outside of the molecule. All the regions on the outside are the same color, indicating the same electron density. So even though we have very electronegative atoms here, fluorine, this molecule is still nonpolar. So how do we determine if a molecule with more than two atoms, a polyatomic molecule, is polar? We've already looked at how to do it for molecules with just two atoms, but what about molecules with more than two? Well, first thing, we always have to check to make sure we are talking about a molecule, not an ionic compound, a metal, a network covalent compound, because those types of compounds and substances, a polarity doesn't apply there. So if we do have a molecule, we must always start by drawing our dot structure. Then we must determine the molecular shape or molecular geometry. Now, once we have all this done, it comes down to two things. To determine if it's polar, we have to determine if our molecular geometry is symmetrical. And then we also have to look at our terminal atoms in the molecule. Are the terminal atoms all the same, or do we have at least one that's different? These two factors are key to determining polarity for polyatomic molecules. So let's define what we mean first by symmetrical molecules. A symmetrical molecule, or symmetrical molecular geometry, is a molecule where all of our bond angles are the same. So with few exceptions, molecules without lone pairs of electrons around the central atom tend to have symmetrical molecular geometries. Those lone pairs, if you have them around the central atom, they tend to push those bonding pairs away a little more and distort them from what we call their ideal bond angles. So that gives us an asymmetrical or non-symmetrical molecule. So let's look at some examples here. If we look at our table of VSEPR geometries, and we've seen these before, let's go through and tell which ones are symmetrical. So if we look here at linear geometry, we see all our bond angles are 180 degrees. We don't have lone pairs on the central atom. That's going to be symmetrical. What about trigonal planar? That's also symmetrical. Everything is 120 degrees apart, no lone pairs. Tetrahedral is also symmetrical. Trigonal bipyramidal is symmetrical. We don't have any lone pairs. Now we do have 90 degree and 120 degrees, but all of our bonds are spaced as far out apart as possible, so that's considered symmetrical. And finally, octahedral, those bond angles are all the same. We have a symmetrical molecule. Now, on the others, you see we have lone pairs around our central atom, and that tends to distort our bond angles from the ideal bond angles, giving us asymmetrical or non-symmetrical geometries. There are a few exceptions, however. If you look carefully, square planar, even we have two lone pairs here, but all of our bond angles are 90 degrees. They're evenly spaced. And then we have two linear shapes. So just looking at the bond angles, not the lone pairs, our bond angles here are 180. They're evenly spaced, just like the linear geometry here. So the ones in blue are symmetrical. The others are non-symmetrical or asymmetrical molecular geometries. So we said there were two things we needed to look at: the symmetry of the shape, the molecular shape, whether it's symmetrical, and the terminal atoms, whether they're the same or different. So let's kind of sum those up. So If we have a non-symmetrical molecular geometry, so non-symmetrical molecules, the electron distribution tends to be unevenly distributed around the molecule, so non-symmetrical molecules tend to be polar. If we have a symmetrical molecule, we also have to look at the terminal atoms. Symmetrical molecules with different terminal atoms, the electron distribution tends to be unevenly distributed around the molecule, giving us, again, polar molecules. So if it's non-symmetrical shape, or if it's symmetrical with different terminal atoms, those tend to give rise to polar molecules. If we have a symmetrical molecule, but the terminal atoms are the same, then we should have an electron distribution that's even around our molecule, giving us a nonpolar molecule. So I've generated a flow chart that I think might be helpful. So let's go through this flow chart, which kind of summarizes the 3 points that we were just looking at here. So the first thing, we always have to check, be sure we're talking about a molecule. So is the substance that we're looking at a molecule? If the answer is no, then polarity does not apply. So if it's an ionic compound, a metal, a network covalent substance, then we don't need to go any further. We can't say it's polar, nonpolar, because polarity doesn't apply. However, if the compound is a molecule, the next question we ask is, does the molecule have more than 2 atoms? And the answer, yes or no. If the answer is no, the molecule does not have more than 2 atoms. It has only 2 atoms. So something like Cl2, HF, HI, something like that. We determine the polarity by calculating the difference in electronegativity. If the difference in electronegativity is 0 to 0.4, nonpolar, 0.5 to 1.9, it's polar, and greater than that, it's ionic. So we have a separate video lecture on how to determine the polarity for diatomic molecules, those with only 2 atoms, because they only have 1 bond. We just look at the difference in electronegativity. But what we want to focus on here are the polyatomic molecules. So does the molecule have more than 2 atoms? If the answer is yes, then we look at the symmetry. Is the molecular shape symmetrical? We define what that means, yes or no. If the molecular shape is not symmetrical, then the molecule is polar. Simple as that. If the molecule is symmetrical, then we have to ask, are all the terminal atoms the same? If the answer is no, they're not all the same, the molecule is polar. If the terminal atoms are all the same, then the molecule is nonpolar. So for molecules with more than 2 atoms, we look at the shape, the symmetrical shape, and the terminal atoms to determine whether it's polar or nonpolar. So let's look at a couple of examples. Let's look at these two, CF4 and CH3F. Now I've already drawn the dot structure and determined the molecular geometries. Here we both have tetrahedral molecular geometries for both of these, and I've got those drawn out here. So let's look at CF4 first and determine if it's polar. So here's CF4. So let's go through. Is this substance a molecule? Yes, it is. It's 2 or more nonmetals bonded together. Does the molecule have more than 2 atoms? 1, 2, 3, 4, 5. Yes, it does. Is the molecular shape symmetrical? Well, we said a tetrahedral molecular geometry is symmetrical, so that answer is yes. Are all the terminal atoms the same? Again, our terminal atoms here are all 4 fluorines, so the answer is yes. So that means this molecule is nonpolar. Okay. Let's look at our other example, CH3F. Is this substance a molecule? Yes, it is. We have 2 or more nonmetals bonded together. Does it have more than 2 atoms? Yes, this is polyatomic. Is the molecular shape symmetrical? We said tetrahedral is a symmetrical shape. Are all the terminal atoms the same? We have 1 fluorine, and then we have 3 hydrogens, so they're not all the same. So the answer is no. That means this would be a polar molecule. Okay, so we know the electron density is going to be unequally distributed here because we have a symmetrical shape, but different terminal atoms. So here's 4 examples. I want you to work each of these. Again, determine if it's a molecule first, draw the dot structures, determine your molecular geometries, and then use that flow chart to see if you can determine if each of these are polar or nonpolar. So write those down. make you a copy of that flow chart, pause the video, and give it a try. Okay, so for each of these, we're going to go through our steps, our flow chart, and see if we can determine if these are polar. Okay. So let's start with CHCl3. Okay, that's our first one. So is this a molecule? Yes, it is. We have nonmetals bonded together. Are there more than two atoms? Yes, there are. Is this a symmetrical shape? It's tetrahedral. The answer is yes. Are all of our terminal atoms the same? No, we have one different. 3 of them are the same. So because our terminal atoms are not the same, this is going to be polar. What about NH3, which is ammonia? Is this a molecule? Yes. Are there more than 2 atoms? Yes, there are 4. Is this a symmetrical shape? This is a trigonal pyramidal shape. With the lone pair here, we're not going to have these bond angles ideal. So therefore, we're going to have an unequal distribution of the electron density. So this is not a symmetrical shape, so we don't have to worry about the terminal atoms. We stop there, and that is polar. What about CO2, carbon dioxide? Yes, it is a molecule. Do we have more than 2 atoms? Yes, we have 3. Is this a symmetrical shape? This is a linear molecular geometry, so it is symmetrical. Are the terminal atoms the same? Yes, they are. So even though we do have oxygen is more electronegative, because it's symmetrical, our terminal atoms are the same, our dipole moments cancel out. So that is nonpolar. And finally, HF. Is this a molecule? Yes. Are there more than 2 atoms? No, there's only 2 atoms here. So here, we don't need to worry about the symmetrical shape or the terminal atoms. So is it polar, nonpolar? Well, we have to look at our difference in electronegativity. Fluorine is 4.0, hydrogen is 2.1. So we calculate the difference in electronegativity here. We get 1.9. That sets us up as a polar molecule. So this one is polar. Now, one more thing that's very important about polar molecules. When we do have a polar molecule, we must determine the net dipole moment for that molecule. Nonpolar molecules do not have a net dipole moment. The net dipole moment determines exactly where the partially negative and partially positive regions are in that polar molecule. So the net dipole moments, once we understand now how to determine if it's polar or not, we'll discuss net dipole moments in a different video lecture. So we'll save that for our next one.